So welcome back, and today we're going to talk about probably my favorite family of instruments, since I personally play a few of them, mostly the saxophone, but a little bit the clarinet and occasionally the recorder. And so I'm going to just start maybe by demonstrating a few of those and kind of emphasizing how different they all sound. So in this family of instruments, we have the flute family that includes recorders and flutes. We have the clarinet family that is an instrument with a reed. And we also have the saxophones, which are similar, single reed instruments. And then we have the oboe and the bassoon. And these are instruments with what we call a double reed, and I'll show you what those are later in the lecture. But they all sound very different. They're all kind of based on the same physical principle that you have a tube and there are standing waves in the tube and you have various harmonics, and the sound is just a combination of those harmonics. So we've understood that, and they all also have the feature that they have various holes that you either cover with your finger or press keys to cover up the holes. And depending on how many holes you cover, that affects the effective length of the instrument. So they all have that in common, but today we're going to talk about some of the finer details of these instruments and how they differ and how they really work, how the sound is produced. So we can start by just listening to a few different examples. Okay, so oops. So I don't play the flute, but I have a recorder. This is my recorder from 3rd grade. I carved my initials in it at some point. So the recorder, like most of these instruments, you can play both the fundamental frequency as well as higher frequencies. And so these correspond to what we call different registers of the instrument. So the recorder starts at this note. So that'd be the lower register. But then you can play stuff up higher. And so that corresponds to making use of the higher harmonics of the instrument, the second harmonic. And I do that by partly either just blowing harder or partly uncovering this hole at the back. And so we'll understand later on what's going on there and why that works. Okay, and so then you have the clarinet, which, as I said, has a reed on it, and it has many buttons, and all of those are really just for opening and closing various holes. So the clarinet also has a low register starting down here. And then you can go up. So that's all the low register using the fundamental frequency for varying lengths of tube. And then you can go up to a higher register, normally by pressing this key at the back. And so that would sound like this. Well, I see I'm exceeding my microphone level here. Hopefully that wasn't sounding too bad. Okay. So I don't really play the clarinet much anymore. I think the upper register is suffering a little bit. And then finally I'll demonstrate the saxophone. And so that's again similar idea with a tube and lots of keys that basically are all about opening and closing holes. And one of the things that you notice right away is that the saxophone is curved. That really doesn't affect the sound that much. It's just that if it weren't curved, it would just be unwieldy and long, especially the larger ones, the tenor saxophones and the baritone saxophones. Okay, so I'll just play a little bit in the lower register and then in the upper register. And then you could actually even play with a saxophone. There's a set of notes called the altissimo register that's getting into even these higher harmonics. So I'll turn down my mic to play those. Okay, so that was all the lower register, and now we'll go up. And we go up even higher. All right, well, I don't practice the altissimo very much, as you could probably tell. Okay. All right, so let's talk about how these instruments, why they're so different from each other, and in terms of the sound. And so, turns out that the flute family, the clarinet, and then the saxophone and oboe and bassoon, those are, in a sense, three different groups, which differ quite a bit in just the basic physics of the tube. So you remember that the musical tones, ultimately, they come from these standing wave oscillations of air inside the tube. And for the flute, it turns out that the way to understand this tube is a tube that's really open at both ends. Even though the flute itself is closed at one end and open at the other, in terms of the standing waves that happen inside the flute, really it's open at the end where you have what's called the tone hole or the embouchure hole. I have a simple wooden flute here. So you see there's a hole here, and I don't cover it up. I would just blow there at the hole. And so it's really open to the air. And then whatever the first open hole is along the flute would be the other end. And so we would have standing waves with an antinode here at this open tone hole and an antinode at the first open hole on the instrument. And so we would have, for example, with the fundamental vibrations of air like that, where you have maximum displacement here, maximum displacement here, and a node in the middle with minimum displacement. So the graph looks like that one. And then if you go ahead and kind of make a graph of the standing wave pattern for the higher possible modes in the tube with antinodes at both ends, then you find that the second one has twice the frequency of the first one, so half the wavelength of the first one, and the third one has 3 times the frequency of the first one. And so you get the entire harmonic series, and you can so you could get if you play the first overtone that's possible, it's just an octave up. So like, sorry, and then the fifth above that. Okay, and then you could, in principle, play higher ones as well. Moving on to the clarinet, that's also like a cylindrical tube, but it's closed at one end. So like the demonstrations that we did earlier with the trumpet type instruments. So the clarinet has a mouthpiece, and that's in your mouth. There's a very small opening, and obviously that's where the air is coming in. But in terms of the motion of the air, it's mostly not moving very much right at that end. And so we can treat it as a closed-ended tube. And then the other end is an open tube, and effectively that starts where your first open tone hole would be. And so if you plot out the waves, then there's these closed open tubes that we saw in some earlier lectures, and you find that the wavelength of this second pattern is 1/3 the wavelength of the first pattern. And so that means that in terms of the frequencies, then the natural frequencies for the clarinet are not the entire harmonic series. It's the fundamental, and then 3 times the fundamental, and 5 times the fundamental, and 7 times the fundamental. Okay, so you can try to play. I'm not sure if I can play easily those on the clarinet, but let's give it a try. So, well, I need help from the. That is what this little hole helps with. It helps isolate the next note, which is the turns out to be the third harmonic. So, okay, so we're going to talk more about that little key and what it does very shortly. And then the third type of instrument here is differing from both of those other two because the actual tube is quite a bit different. If you look at either the picture or the actual saxophone here. So this in the picture is a soprano saxophone, and then if you look at this one, it's the alto saxophone. And what you notice is that tube actually gets wider and wider and wider as you go along it. Okay, and so that is, don't fall. All right, putting my sax on the stand there. So that's what we call a conical tube for obvious reasons. It's shaped like a cone. And it turns out that that has interesting consequences for the physics. So even though this is a closed open tube, it means really just like the clarinet, the fact that it is conical instead of mostly just cylindrical with a constant thickness. So here the thickness increases along the length of the tube. That means that even though you get similar kinds of standing wave patterns to the clarinet, so you get a pattern with no nodes like this, and 1 node and 2 nodes, well, you notice that these are no longer kind of perfect sinusoidal shapes. So for example, the distance between the nodes is not the same, especially if you look at that third one or the higher ones. And if you study this problem, this involves the physics of waves in 2 dimensions, because you have to take into account the fact that things are changing along the direction of the tube. And so what you find is that kind of magically, instead of F and 3F and 5F, with a conical tube like this, you get F and 2F and 3F. So actually, again, you get the entire harmonic series. So with a saxophone, then you can just, keep your fingers in the same place. So I'll cover up most of the holes, and then just using my mouth, I can play these different notes. I'll just try to play the fundamental and the second harmonic and the third harmonic. So normally playing a saxophone, you wouldn't be playing those harmonics without changing your fingering. So as with a trumpet, then you are definitely just playing all of the harmonics in order to get various notes. But with a saxophone, usually you're using keys. Even if I want to go up an octave, there's a key to help with that. And so those notes, as you might have heard, they weren't particularly stable, and they're a little bit difficult to play the harmonics without changing the fingering. But anyways, you can hear that they're there, and they are natural vibration frequencies in the saxophone. Okay, so I want to talk a little bit about the register holes, and then so how to go between these different playing the fundamentals and playing the harmonics in an instrument like the clarinet or the saxophone. And then I also want to get into talking about how the sounds are produced. How are these reeds working, and how do you produce the sound in a flute? And so in order to understand both of these things, we want to go back and just remember something about how the displacement of the air in the tube. So we were seeing these patterns of displacement for the air in the tube. We want to understand how that would be related to the pressure variation in the tube. So I have a little question for you to think about. I think I probably talked about this at some point, but I'm sure it's rusty by now. The question is, if I have an open closed tube, like the ones I've drawn here, and if I have a standing wave in the open closed tube, so that's basically what I've pictured, and the red arrows show the displacement of air, sort of the motion of the air molecules, and the black dots are sort of representing the air molecules. What I want you to think about is either at the closed end of the tube or at the open end of the tube, what do the pressure variations look like? So in both cases, you're going to have some pressure as a function of time, and it might or might not be equal to the atmospheric pressure. Sometimes it might be higher and lower. So I want to know, at these two different places, are the pressure variations large or small, or large in one place and small in the other place? Okay, so hopefully you've had a chance to think about that. And what I want to do now is explain the answer. And the answer is this. So large at the closed end and small at the open end. And in order to understand this, the easiest thing we can do is just look at the diagram. So let's start with the closed end. And what we know is that at the closed end, you have a node for the displacement. The air can't really go back and forth across that closed end because it's closed. But what does happen is that when you have the standing wave, some of the molecules, let's start from the bottom picture. So some of the molecules close to the end, they will be oscillating, and then they'll go towards that end, and then they'll bunch up there at the end, and after a little while, they'll go back. And so the oscillations of molecules near that end will result in this pattern where the density gets higher, and then lower, and then higher, and then lower. Okay, and so remembering our relation between pressure and density, the higher density of air molecules we have, the bigger the pressure is going to be. Okay, so it's like they all rush in. Now there's a lot of them. Then there's a high pressure, and that pressure pushes them back out. And then this other region of high pressure pushes them back in. And so that's how our standing wave works. Okay, so at the closed end, we have a node for the wave, for the displacement. The air molecules aren't moving right at that end, but the pressure is changing a lot right at that end. What about the other end? Well, so the other end is the opposite. The other end has a lot of motion of the molecules. You can see that's the place where they're going in and out the most. But it's actually one of these places that's right in between the locations where you have maximum pressure and minimum pressure. And so like this one alternates between lots of pressure and low pressure. This one alternates between low pressure and lots of pressure. And then the places in between actually maintain pretty much the same pressure all along. And this part at the end is one of those places. And there's a reason for that. There's a reason why the pressure at the open end of the tube is staying pretty much the same. And that is because it is open to the surrounding air, which is like just a large reservoir of air with a certain fixed pressure. And so if you have the end of the tube and it's open to that region of a constant atmospheric pressure, then that end of the tube is going to be pretty much that same pressure as well, just because it's in contact with the big pressure reservoir. Okay, so that's how you can understand that at the open end of a tube, even though that's where the air is moving in and out a lot and producing the sound wave, the pressure is not really changing much. Whereas at the closed end, where the air is not moving, then you get a large variation in pressure. Okay, so I want to use that then to explain a few things about these woodwind instruments. Okay, so the first one is then how this register hole works. So what is going on when I press this key here on the clarinet? Let me just zoom to where I can see what I'm doing. Okay, yeah, so you'll notice if I zoom in a lot, here we go. So when I open that, there's like a tiny little hole. There it is. So zoomed in so it looks bigger. So there's a little hole that opens when I press on this register key. And so what that is doing is basically opening a little part of my clarinet in the middle to the outside air. And it's a tiny little hole. So it doesn't kind of effectively end, it doesn't act as one of these holes that effectively ends the tube. So there's still a wave going on either side of that hole. But what it does is it ends up suppressing the fundamental mode of vibration and favoring this next mode, which is actually in the clarinet. I should probably call it the third harmonic because it's 3 times the frequency. Okay, so how does it do that? Well, if you look at the fundamental mode, then there's sort of large pressure variations all along, except at the very end of the tube. Whereas if you look at this harmonic, and you notice in the middle, there's this point where the pressure isn't varying. So this is what we'd call a pressure node. The pressure stays constant at that point when you have that first harmonic oscillating. So again, it should be probably the second harmonic when you have that one oscillating inside the clarinet. So what we can do is open that hole, which is at the location of this point. And what that does is it kind of forces the pressure at that point to be pretty much constant and pretty much the same as the outside air pressure. And what that then means is that you no longer can have this fundamental mode. You can't play that note anymore because that note has pressure at this point varying a lot. And so it's like we're forcing the pressure not to vary a lot. So we're no longer allowed to have this mode, but we can still have this mode because that already has a pressure node at this point. Okay, so if this reminds you of something, that's good. It's almost exactly the same as the way that we played harmonics on a guitar. So let me just remind you of that. So with the guitar, again, we had various harmonics, and the way that we could play, say the second harmonic on the guitar was actually just to put our finger gently on the place on the guitar string where that second harmonic has a node. Okay, and that suppresses the fundamental because the fundamental moves around a lot at that point, and if we stop the string from moving at that point, you can no longer play the fundamental. So it's just like that, except we're forcing the pressure to be constant at that point by opening this little tone hole, and then we're getting that harmonic instead of the fundamental. Okay, so I think I just said all of that already. So just a quick skill testing question. When I do that on a clarinet, see if you can figure out what note I'm going to get relative to the note that I started with. So I'll give you a minute to think about that, or pause the video and then I'll explain it. So, all right, so let's actually demonstrate it first. So I'll play a note and then I'll press the octave key and then we'll hear what new note we get. Or I'll play a different one. All right, so if you're musically inclined, you might have heard that the right answer is an octave plus a fifth. And the way to understand that is to put together a few things that we've learned recently. So the first thing is that when we open that register hole, we understood that you're suppressing the fundamental, so you're getting that next mode of vibration, which for a clarinet is 3 times the frequency. And so then if you start with a note and then you go to a note which is 3 times the frequency, what is that note? Okay, well, first we could think about going to 2 times the frequency, which is an octave above. And then you could think about going to 3 times the frequency. So that's 3/2 of the new frequency, and that is the interval of a fifth. So you go up an octave and then you go up another fifth, and that gets you a note which is 3 times the frequency. Okay, so that registry key on the clarinet, it's not an octave key like it is on the saxophone. It's an octave plus a fifth higher. And when I was playing the clarinet and then I switched to the saxophone, I was thinking, well, it's way better to have the octave key just go up an octave. Why didn't they do that for the clarinet? But the answer is that, well, the clarinet is a cylindrical tube, and it's the first overtone that you play on the clarinet is the octave plus the fifth. It's really the third harmonic. So you don't really have any choice. Okay. Whereas with the saxophone, I'll just show you the octave key on the saxophone. Going back to, all right, yeah, so the octave key on the saxophone, it's actually pretty interesting because it opens different holes depending on what note you're playing. So if you're playing a lower note, okay, there we go. Let's see, the tiniest little, there it is. So you can see it open. So the octave key opens that hole there. But if I am playing up high, if I play a higher note, well then the pressure, the instrument is shorter, and so the pressure note is actually for that first harmonic, the pressure note is way up on the neck. And so you see for the high notes, if you play the octave key, then it opens this one way up on the neck. Okay, so I think I will stop there for this video. And then in the next video, what I'm going to do is talk about what's going on with your mouth. How are you actually producing the sound in the saxophone or in the oboe or in the flute?